tries to estimate failure rates for devices. That is also a multiplicative type of model. And in multiplicative model, assumption is that defect density is given by a set of factors that you multiply, and these factors depend on some factors. So for example, here this is some factor of 1. Okay, I'm using the term factor with two different meanings here. So by factor I mean a thing that you multiply in a mathematical expression, and by other factor I mean factors that control defect density. So sorry about using the one identical word with two different meanings at the same time, but I guess in the context that should be clear. So some factor of 1, perhaps this has to do with programmer skill, and then there's a factor 2, which is maybe some has to do with programming environment, and another factor, and so on. So basic idea is, so some factor may increase the defect density by a factor of, let's say, 1.25, or may decrease it, and it might cause a multiplication by 0.70 and so on. So default value of these would be taken to be 1. So if you don't know about a factor, the default value of the factor would be 1, and hence you don't have to worry about it. So basically you just take the typical value, and this is a constant here. Now let us take a look at a model, and this is the model that we came up with, and it is a multiplicative model. So here is a model. So this is a static defect density model. And so we worked on it for a while. And actually, there's a lot of research still going on, because there's a lot of questions that have not been answered, a lot of disagreements. But let me share what I have found. And here's what we propose. That defect density is given by some constant. Now you have to estimate this constant by applying this model. And you can estimate C using some given data. So so we thought about, okay, what are the factors that, based on the available literature, that actually do impact the defect density. So one of the factors is a phase factor, and I'm going to talk about it in detail. Depending on what phase of the development and testing you are in, the defect density is going to be different. And you have then programming team factor, so let me call it F sub PT. And there's a process maturity factor, let me call it F sub M. So this is the phase factor, and it is the programming team. Capability of programming team. M is the process maturity. And Fs is structure. Structure of the software. And John Musa suggested that we put in a factor for requirement volatility. Now this is related to what some people call code churn. And we decided that this is a fairly complete list, and different factors can somehow be made part of these factors. So now the challenge is to figure out what are these factors. So what happens to the phase which will cause defect density to be multiplied by a certain factor? And default value of each is 1. So if you don't know about a certain factor, assume that it is the typical value and the typical situation, and the typical, if for a typical situation, the value is 1. Okay, so let's look at these, and let's look at the phase factor. Now you have heard about phases of software testing, or maybe not. I guess if you are in computer science, you have heard about software testing phases, but if you are in electrical engineering, you probably may not have heard. And let me give you some, okay, I'm going to give you a table. So let's look at the phase factor. At the beginning of phase, multiplier. Incidentally, in this course, there's always a dilemma because we have both computer scientists and electrical engineers. So what should this course be? And I take the view that a lot of concepts are really common. So I think hardware people will benefit by knowing more about software, and software people will benefit by knowing what the hardware people know. And in fact, it turns out that some of the concepts have gone from one field to other fields. So for example, in testability is a concept that has been around in hardware for quite a while. In software, it is more recent. So they actually got it from hardware. And then there have been ideas that have gone the other way. And of course, these days, a lot of times what the engineers do involves software. So a lot of electrical engineers, they are actually, now when we think of electrical engineers, what do? They work on the machines, take out parts and tighten nuts and things like that. No, actually what engineers do most of the time is do calculations, right? Design things, analyze designs. So they are basically, a lot of time they are actually working with software. So unit testing. Now, at the beginning, in the standard software development methodology, if I can call it standard, because there's a lot of controversy there. So the assumption, so usually people will divide the software to be developed into small pieces of functionality, and they will write a small piece of code, write another piece of code, and these will be called units. And these small pieces of code would be tested initially. So this is at the beginning of the unit testing. Let us make the multiplier 4. So the defect density is 4 times the default value. And there is subsystem testing. Now during subsystem testing, what you are doing is taking these units and connecting them together. So that you are basically integrating the system in testing. So this is testing going on when you are connecting these subsystem testing. So during this phase, some testing has already been done, right? And as a result of this, at the beginning of subsystem testing phase, defect density could be given by a factor of 2.5. And then there is system testing.
So, excuse me. The factor 2.5, is it 2.5 of the original value or 2.5 of the previous?
2.5 of the default value, and let us assume that this is the default value. So basically, so let us assume that when people collect data, they collect data at the beginning of system testing phase. So basically, we are comparing this and this with the beginning of system testing phase. It's a relative number. And after system testing, you have operation. So you have done your system testing, and you released it, and it is operational. Your defect density is would be multiplied by a factor of 0.35. Okay, how did we come up with these numbers? Okay, first of all, in different situations, obviously the numbers are going to be different. But this is the kind of numbers we have come across in literature. So we looked at some data that was collected by John Musa, who was a pioneer in software reliability engineering. He passed away a couple of years ago. So he was actually responsible for collecting some of the early data back in the 70s. And the discipline, there was some work done before him, but he was able to make it, create it into a systematic discipline. And as I was mentioning, so we added this on the suggestion of John Musa. He thought it would be a good thing to add, and I will talk about it. So, yeah, so I was mentioning, and there was some data that was given by Gaffney, there was some data given by Pivovarsky. So these are different people from different organizations. And we sort of averaged the numbers. So this is to give you an idea of what kind of numbers you may see. I cannot guarantee that this is what you will find, but this is the kind of stuff we have seen, to give you an idea. So notice that it is important to know when you talk about defect density of this software is this, you have to know what phase we are talking about. Because at the beginning of subsystem testing phase, defect density would be much higher. At the beginning of system testing phase, defect density would be less. And defect density, of course, would be even less after you have done some good system testing. So this we are taking as, we took this as a default level for comparison. Okay, now let us come to the second factor. Any questions on this or comments? Now let us consider the programming team skill factor. Okay, so FPT. Now, do you think the programmers, they all are same, or are they? So they actually differ quite a bit in terms of capabilities, and there are some programmers who are really good. They like really good programs. Nobody writes fault-free programs. I've seen claims, but I don't believe them. And neither should you. But nobody writes fault-free programs. However, there are some people who will who tend to write a program with much fewer faults than some others. Yeah. And it is a function of a number of things, and some of the things are very hard to measure. So this is, even though this is a very interesting topic, the thing is you are measuring people, and people don't like to be measured. As students, you don't have a choice. So you have to take a test, right?